So most of the plastics that we are using, they are made of polymers. And as the polymers are made from some of the organic compounds, many of the polymers are chemically unreactive as well. We said that when they have in the alkanes, we said that when they have carbon-carbon single bond, the carbon-carbon single bond is unreactive. In addition polymer, we said that alkene is going to break the double bond and make single. Means the final polymer is alkane now, having single bond. Single bond means it's chemically unreactive. So maximum of the polymers which are made are basically chemically unreactive. It means the polymers are going to be non-biodegradable. What does mean by non-biodegradable? Any idea you have before about biodegradable or non-biodegradable word? Anyone? Yes, Luna.
Miss, I have like short idea. Miss, not biodegradable. Um, it means it's unrecyclable, like cannot be used again in life,
Mhm. Okay.
something like that, or cannot be
Uh,
broken down, or something like that.
The second point is fine, cannot be broken down. Okay. Recycle or not recyclable one is a little different thing. So we'll talk about this. Yes, Wafia, your point of view about biodegradable or non-biodegradable?
Miss, it's similar to what Luna said. So biodegradable means it can be, quote, decomposed by like bacteria and living organisms feeding off of it, but non-biodegradable is the opposite. So,
Hmm.
it's the long-lasting sort of plastic to put it like
Okay,
simply.
right. Yes, Arish, you were raising hand.
Yeah, I wanted to answer. It's
Hmm.
my answer is similar as well, that biodegradable material is something that can be broken down, um, but
Okay,
the other one
right.
cannot.
So this definition is fine that we can decompose them or we can break them. So biodegradable is the polymer which can break down into smaller pieces and it can easily be wasted. Non-biodegradable is the one which cannot broken down into pieces by any chemical reaction because they're chemically unreactive. So it means we cannot waste them. The simple plastic water bottles that we use, basically maximum are made from non-biodegradable polymers. It means if you throw the water bottle in a sea, or if you just put it underground, you just bury it in the ground, wherever you're going to just throw it, it is not going to break into pieces even after many many years because it is chemically unreactive and non-biodegradable. So it has many of the drawbacks as we will talk about them, about the environmental issues, that non-biodegradable polymers, their disposal is very hard, means they can cause many problems related to environment. Okay, how we can dispose them then? If they're not, like, say, let's say, are reacting, if we are going to throw the water bottle, it is not reacting with the water in the sea, means it cannot break down. It is not reacting with the microorganisms, the bacteria, when we just bury it underground, it means it is not reacting with microorganisms. So it is not reacting with anything to break down. So then how we can waste this type of the plastic material? We have number one method, we can do incineration. Incineration means heating. Heating at very, very high temperature is known as incineration process. It's just like a modified form of heating. So heating at high temperature is known as incineration. So we can heat the polymers or we can burn the polymers. But when we burn this type of the polymer, like the plastic material, it is going to produce a lot of carbon dioxide because they are made of organic compounds. So when we burn them, we are going to do its combustion reaction. They are going to produce a lot of carbon dioxide. This carbon dioxide can be added to the environment, which is a greenhouse gas, and that is going to cause a lot of uh, issues to the environment, like the climate change. We cannot heat or burn all the polymers. It will not be good for the environment. Okay. Then some polymers can release other gases as well. Before that, yes, your question, Wafia.
Miss, I wanted to ask that sometimes there's like some specific, plastic boxes where people usually advise us to not put them in the microwave. So is this the reason why some plastic boxes
Yes,
aren't,
yes.
safe to put?
Because
No.
some of the plastics, they are going to release carbon dioxide when we just give them little high temperature, and some can even release very, very toxic gas. Like some polymers release the toxic fumes when we burn them, and that toxic fumes are of toxic hydrogen chloride gas. If your polymer is made up of polyvinyl chloride, if your plastic, and most of the plastics are made from PVC, okay? Its short form is P for poly, V is vinyl, C is chloride, PVC plastic. Maybe you have heard the name PVC. And it's written on maximum of the plastic materials. If you see the plastic bottles, not the water bottles, like the shampoo bottle, sometime the conditioner or the water pipes, many where you will see the PVC word written, polyvinyl chloride plastic. If you have polyvinyl chloride plastic and you heat it or burn it, it can release a toxic hydrogen chloride gas. So that is the reason we cannot put them under the high temperature, heat, microwave, or we cannot burn them because they're releasing some of toxic gases. And if we just incinerate or heat them with incomplete combustion, means limited oxygen, then we know incomplete combustion release also a very toxic gas, carbon monoxide. Okay, so heating the plastic is not going to solve the problem. By heating, we can dispose them. We can just remove them from the environment, but they are adding some toxic gases to the environment. So it means they're wasting them by heating is not a solution. Okay, there is another way, and that is we can just throw them in the ocean, and that is going to accumulate. All the plastic can just accumulate in the ocean, and that is going to just harm the aquatic life. It is not the solution as well. We can throw them under the soil. Okay, landfills means we are just throwing them in the soil. We can throw them in the soil, but if the plastic is not going to break down, it means it will stay over there, and it is going to just increase the amount of garbage, and all the land can quickly fill up with this type of the plastic. So it means we are using the a very good amount of land we are using just to throw the plastic material. So the land is going to fill up quickly if we are going to do this practice. So throwing them in the ground or in the ocean or heating them, all these three are not the solution. They are creating environmental issues. Okay. Before
Miss,
that, yes, your question, Luna.
no question. I have a solution.
Yes, your solution then.
Miss, instead of throwing them, which
Hmm.
causes global warming and everything, Miss, why don't we start from the beginning, from the point zero, where they were actually created?
Right.
So we can do one thing. We can do some
Hmm.
chemical tests, some chemical thingies. I don't know what you do.
Okay.
Whatever
Okay.
scientists do.
Hmm.
Whatever scientists do. And return them to their original form. For example, if they were for example, carboxylic acid with, I
Hmm.
don't know, maybe ester together, if they put
Hmm.
together, we can um we can break them
Can just
down
change the
and
structure you're asking and make them reactive one so that when we
yes, we
dispose
can.
them they can break, and that's a good idea. Yes, that's what is the solution at the end. So rather
See?
than making the polymers by addition polymerization, because addition polymers are mostly unreactive, condensation polymers can react because they are functional groups inside. So rather than making the plastic by addition polymer, make the plastic by condensation polymer or those groups which are reactive. Automatically, when you are going to throw them in the sea, in the water, land, or whatever, they will automatically break. So that is the solution Luna told us. That's a good solution. Yes, Samreen, your point of view. Or any question here?
Miss, I have a question. Miss,
Hmm.
what happens if we come into contact with toxic hydrogen chloride gas?
Toxic hydrogen chloride gas fumes can go and give you some lungs problem and like your breathing issues. Okay.
Oh, okay.
Mm. Yes, Wafia.
Miss, I've got two questions. So first of
Okay.
all, what's microwavable packaging, like microwavable plastic packaging made of?
What is the micro your question again? I did not get the question.
Miss, what's like plastic microwavable packaging made of? Like the boxes and,
So the box is
wrappers that you can,
that
the
is
ones that
not
you can microwave.
plastic basically. Most of the boxes that we use, the shiny one, silver one, it's aluminum. They are made from aluminum. The plastic material that we use, they are made from addition polymers. So that is the reason they always ask you not to microwave the things in the plastic boxes because they're made from addition polymerization. Okay. But the one that we can use, the silver color one, the box, that is basically the aluminum material. That is fine. We can heat in the aluminum material. Okay. But we cannot heat them in the addition polymers.
But Miss, sometimes I've seen some plastic boxes that say microwave oven safe on them.
They are
Miss,
made
So,
just
from, then it means
Miss,
they are made from the polymer which is safe, which is not reacting at 100 degrees Celsius or 90 degrees Celsius, which is the temperature of microwave. So some
Miss,
polymers are not
right,
affected till 190, 150 temperature. So they are safe. If we just heat them, put them in the microwave, they will not break their bonds or react.
Miss,
right,
Okay.
okay.
So it depends upon their temperature, at what temperature they can decompose the structure. So the plastic material and their temperature values will tell us how much temperature heat they can bear. Okay. Yes, Luna.
Miss, I used to have one of those.
What?
And for God, wallah alhamd, for God's sake, I have these microwavable caps that you put in the microwave. They're usually used for coverage of the food. One day I put
Yeah.
it there. I don't know what temperature I put in. It just microwave down, and I literally burned the microwave, and I had to buy
It's
another one.
very dangerous. So whatever material you're
Yeah,
using,
and
be careful and be sure about the material if we should put it in the microwave or no. Okay.
it makes nobody told me that when I was younger. This is the third
Mhm.
microwave that we have. Nobody told me when I was younger. So
Okay, okay. So it was a bad experience. Okay,
yes,
let's move forward.
lesson
This is one of
learned.
the example. Yes, Wafi, is
Miss,
any question?
yes, Miss, I'm so sorry, but I have another
No
question.
problem. Yes, ask.
I was thinking, hypothetically, if all of the plastic, that's disposed in this world, hypothetically, if all of it was glass, so how are you to, like, dispose of glass?
For the glass, we have many solutions. We can melt the glass. We are not going to dispose it of. We are going to recycle it. Even for this plastic, which is chemically unreactive, there is another solution. Recycle it. Take it, collect all the plastic. Don't throw it. Collect it, make some other material from this plastic. Use it again and again. For the glass material, something is made up of glass, no need to throw it. Collect the glass, melt the glass, and make some new materials out of the glass. We can clean them, wash them, put the colors, and we can use it again and again to make some other material.
Miss, we can literally make
Yeah,
glass statues, beautiful glass statues, and
Yeah.
everything.
So for the glass, for the plastic, there is a solution. Just recycle it, reuse it again and again rather than throwing it. It will save the money. It will not create any wastage as well. So that is one solution as well. Okay. So let's move to the more thingy about the disposal. Let's say you have the PET polymer. We said that PET is one of the condensation polymer. It is the polyester. So PET polymer, a condensation polymer which is made up of ester group, so it's polyester or terylene, we can say another name for this. We can dispose it of. It has some reactive groups inside. So if we just provide a little high temperature and high pressure, this can easily decompose. It can break back into its monomers. Okay. But there is a problem that if we just take this polymer, heat it, break it back, it is little hard to get the monomers in the original form. the monomers that they are going to make will be unstable. Means we will not be able to get the monomers in their original stable form. It means we cannot connect them together to make a polymer again. This process will be little hard to go back. So why we are disposing them? Like we have a polymer, we can break it back into its monomers when we don't need it. Then collect the monomers, make the polymer again. That should be recycling again and again, reuse again and again. But in case of the PET, at little high temperature and pressure, we can just break it down. These are the conditions needed to break it down. But when it is going to break into monomers, its monomers are unstable. So it means they will not be relatively, like it's not very easy to make the polymer back. So if somehow we achieve the conditions like they're stable, then we can just convert them back. Okay, then we can just collect their monomers and convert them back. But most of the time, if the monomers that is going to be unstable, this is going to be a small challenge to control the conditions in a way that we can convert it back again and again. So this is called repolymerization. Polymerization means making polymers one time. Repolymerization means we are breaking back into monomers, then we are converting again into polymer. So repolymerization to make new PET again and again is one of the solution. Okay, so to achieve this repolymerization, we need high temperature and pressure. We also need some solvents, which is going to behave like a catalyst, and a little heating over here is needed to just do this whole process. Sometimes enzymes are needed for some specific polymers as well to break it, and then we have to connect them together. So different conditions are needed. This is going to save the resources and energy because we are going to use it again. And one important point over here is it is going to reduce the carbon footprint of the production process. Now, this question will come in your mind. What does mean by carbon footprint? A definition I have already added over here that you can write with you. Carbon footprint means carbon dioxide. It's just an advanced name of carbon dioxide amount. It means when we are going to use this PET again and again, it means we are not doing the heating, we are not going to do the combustion, no carbon dioxide is produced. So means less carbon dioxide or less amount of waste will be created. Okay, so it is reducing the carbon footprint. It means it is reducing the amount of carbon dioxide and other greenhouse gases released into the atmosphere, means no climate change. So this definition of carbon footprint, you can write with you. Let's, Luna, you have any question? Yes? Oh.
Miss? Yes.
Mhm.
Wait, but Miss isn't using big machines for turning into monomers, since you said that turning polymers into monomers is kind of hard and they have
Mhm.
to use machines. Don't they also use like energy, carbon dioxide, and everything to do that? So not
Mhm.
reducing. So
So
it's not really
it will
reducing.
need energy as well, but it is basically using some of the energy but giving us the same polymer again. So saving the money as well. Like we can put
Mm,
some money, some energy, but we are getting the polymer again rather than throwing the
mm.
polymer. Okay. So somehow it is saving the resources and energy. By applying some amount of energy, some amount we can get it, we are getting more benefit at the end. Okay. So repolymerization of the PET, one of the example is given to you. You can start from this one. Okay, you have a dicarboxylic acid and a diol. It is connecting together to make this polyester, which is PET, okay, by condensation polymerization. Now, this PET, you can apply heat, temperature, pressure, whatever conditions are needed with the help of catalyst. Okay. So this PET, let's say, is used to make the bottle. Fine. What you can do, you can apply the heat or catalyst. How much? Maybe 200 degrees Celsius and plus any solvent as a catalyst. Or maybe you can use enzymes, any conditions from these two. So you can break the bond of this ester one from here. Again, you will get the dicarboxylic and diol back. So this is going to happen again and again in a circle. We can make the polymer, then provide the conditions, break it back into the monomers, then monomers can combine together, make the polymer again. So repolymerization of this type of the polymer is relatively easy and it is good for the environment. Rather than heating it, breaking it, disposing it into the environment, it's better to just do the repolymerization. Yes, Samreen.
Isn't this process expensive because it needs high temperatures and pressure?
See, it needs 200 degrees Celsius, which is not very expensive to achieve, plus some amount of catalyst. Let's say you are investing 10% of the amount, 90% of the polymer you are getting back means you are saving a lot of money. You can just use the same polymer again, which is saving a lot of money.
Mm.
Okay, so by putting some starting amount on catalyst and temperature, you are going to get the same polymer again, which was expensive. Rather than throwing, you are getting the polymer back.
Miss, I
Okay.
have another question as well. It's
Yes.
saying in the points there was a one point that high temperatures and pressures can degrade the monomers. So isn't that a problem?
Yeah, it's a problem. So it means we have to control it. Let's say if 200 degrees Celsius is needed, we cannot give more than 200.
So Miss, there's a
If we
fixed
are giving,
temperature
let's say
controlling on.
250 or 300, then it will degrade the monomer, means we will not get dicarboxylic acid. It will break into small, small pieces. So we can do multiple
Miss,
tests. Let's say you are taking one polymer, provide 100. Okay, is it breaking or no? To the monomers only, not to any other thing. Then just provide 200, 300, do multiple tests and see at what temperature value it is giving you original monomers and not giving you anything else,
Oh,
not
okay.
breaking the monomer structure. So suitable temperature and pressure is very important. Giving them very high temperature pressure will break the monomer. So
Hmm.
suitable temperature, pressure, catalyst conditions are very important to get the repolymerization back.
Okay,
Okay.
Miss.
Yes, Luna,
Miss,
your question.
Miss, will a 1 degree, 2 degree will affect for the monomers? Like,
No,
will
one
they?
degree, 2 degree is nothing. It's like very cold.
Right?
Yeah.
It's
Little high
very rare.
temperatures are needed to break them or do anything. Okay.
Mm, okay.
We are moving to one of the previous polymers. All that we said, they are synthetic polymers. Synthetic means we are making them. There is one natural polymer in your bodies that is already there. That is protein. Protein is
Biology.
also condensation polymer, not addition. Here, the Wafia asked one question at the start, that can a monomer have only one carboxylic acid or one amine group? Yes. Now we are going to talk about the same example, having the monomer having one carboxylic acid or one amine group. Okay. So first of all, protein is going to be natural polymers. All the previous polymer that we said, they were synthetic, like we were making them. So this is the only example that is natural polymers. And they are condensation polymer, means they don't have carbon-carbon double bond, but they have the functional group. Now for this, they are basically made from amino acids. I hope you studied the amino acid structure in biology as well, so it will be easy to understand. For the amino acid, you have one carbon at the center. One side is NH2 always, other side is COOH, third side is H, they are fixed. Only this R group means you can add anything over here. It can be any group in place of this R. It can be H in place of this R. It can be CH3 in place of this R. It can be anything else. We have 20 different possibilities that we can add, 20 different R groups we can add. So depending upon 20 different R groups, we have 20 different amino acids. Okay, this R group can be anything. So we are not concerned about this R group. What is this? We are concerned about the functional group. Now you can see one amino acid has one amine group and one carboxylic acid, both in the same structure. All the polymers that we said before, one was having carboxylic acid on both sides, other was having amine group on both sides. But in the amino acid, it's little different. One amino acid has both the groups. On one side carboxylic acid, one side amine group. No problem. take two amino acids together and they can connect from two different functional groups. Okay, before that, yes, Wafia, your question?
So, Miss, in place of R, are you going to have like some specific elements or are you going to have a functional group?
No, it can be some specific groups. It can be functional group as well. In place of the R, it can be NH2. In place of the R, it can be COOH as well. If it is NH2 here, it means there are two NH2 in the structure. If there is COOH in place of the R, it means there are two COOH. It can be simple H, CH3, C2H5, 20 different possibilities are there. So 20 natural amino acids we have depending upon our groups.
So, Miss, we don't have to know
No.
what's in
That is your
place of R.
biology part, and it's not like IGCSE syllabus. Later on, you will remember the 20 R groups, but not now. In chemistry, no. Just remember our group can be anything. You are just concerned about these two different functional groups for chemistry, that this side is amine group, this side is carboxylic acid. Okay. Okay. Amine group and carboxylic acid. Are they going to make amide or ester when they will connect together? Are they going to make a polyester or polyamide at the end? Yes, Lona.
Miss polyamide.
Polyamide, they have to make polyamide, yes. So let's see how they can make polyamide. Before that, these different amino acids, like 20 different types of amino acids are there. Any amino acid, they can just connect together, make long chain, because one amino acid means it's a one monomer. So different monomers or different amino acids can connect together to make proteins. Protein is the polymer, amino acid is the monomer. How many? Between 60 to 600 amino acids can connect together and make proteins. Why they have given you a specific number? Because less than 60 is not going to be protein. That is going to be dipeptides, polypeptides, and other peptides. And more than 60 till 600 is like the maximum limit to join together to make proteins. So in your body, if 60 to 600 amino acids connect together, only then it is going to be a protein. Less than 60 is not the protein, that is polypeptides, like other groups, other things. They will not behave like a protein. Okay, so now let's see how they're making the protein. Let's check out, this is the first amino acid, monomer. Same can come over here, no problem. Same can come or different can come as well. Okay, but the functional group which are connecting together, they should be different. If the first monomer or amino acid is giving NH2, the second monomer or amino acid will not give NH2, it will give COOH then. Because if two NH2 will come closer, they will not release water molecule. If two carboxylic acid will come together, they will not release water as well. So one amine and one carboxylic acid should come closer together to release water molecule. So every amine can release like HH group, and every carboxylic acid can release OH. We know about this. So they can release the water from the center and they can connect together. If only two are connecting, no need to put any bracket on the side. But if many are connecting, then you will remove this H and OH as well. You will put a square bracket on the side and then the number and whatever is given. So if more than two are connecting, okay? So if only two are connecting, then no bracket. But if more than two are connecting, then there is a bracket. So they are going to just react the simple condensation polymer reaction. Condensation polymers are going to form. We have CONH at the center means there is amide link. For the proteins, we also say it peptide link. Peptide is an other name of amide, nothing else. Can say it peptide link or amide link, both is going to be the same thing. Same thing, have two different names. Okay. Yes, Wafia, your question?
Miss, I think this is because I wasn't able to join earlier, but Miss, what's the thing with the square brackets and N?
Okay, for this, you will just check out the first part of the recording, okay? That is how to write the polymer.
Alright,
Okay?
okay.
Problem. Okay, let's move over here. Now, this is one small part given to you from one of the protein structure. This is not the complete protein. Why? It's continue. You can see it's not closed from both sides. It's continue, so it's a part given to you. From this part, you can see how many amino acids you can see connected together. Any idea? The boxes will help you to identify how many amino acids are connected together. Yes, Luna?
Miss, depending on what am I seeing, it's 3.
3.
3.
Okay. This box, and this box is telling you total 3 amino acids are connected. Are these 3 amino acids same or different?
Different because of the colors.
Because of the color. Very good. It means the first and third is not even same in this one. First is a different amino acid, then the second is a different one, third is the different one. Maybe here it's 2 carbon, 4 carbon, 5 carbon, we don't know. So box color is telling you there are 3 different amino acids connected to make this part of the protein polymer. Okay? Okay. And that's the end. You can have any 2 different amino acids connected together and you can just try to make this polymer structure. And remember, proteins are natural polymers and they are the condensation polymers and they are going to be polyamides. Okay? Yes, Samri.
Miss, why are there like 3 different colors of like amino acids
Yeah,
in the
it's 3
in
different
the
colors because maybe the first amino acid have a different R group, the second have a different R group, and third have a different R.
So miss, they will repeat it like after this third one, there will be
It
another
depends.
box which
It
will be a
depends.
dark one. It will
Yeah,
depend.
it depends. It depends. Maybe it is repeating or no. In biology, you will see this structure like in your higher grades later in grade 11, that when you are going to check out the protein have a specific pattern of amino acid, how they can repeat. Maybe the first one is repeating after 30 amino acids again. The second one is coming
Mhm.
after 20 again. So there is a pattern when how they can repeat. Maybe the first and third is same. Maybe the first and the 17th one is same. So it depends
Mhm.
which different amino acids can connect together to make a polymer pattern, protein
Oh,
pattern. So
okay,
all the
miss.
proteins, we have many proteins in our body. Every protein has a different function. Their function depend upon this amino acid sequence. And they all have different amino acid sequence. Okay. Yes, Wafia, your question?
So, Miss, to make a protein, it doesn't have to have one same kind of amino acid in like a long chain. It can be like, let's say, all the 20 types of amino acids in one long chain.
They can, yes, all the 20 can be in one, or maybe only 3 of the 20 amino acids are coming again and again. First, second, third, then first, second, third, then first, second, third. Or maybe 10 are coming, then 10 are repeating, 10 are repeating this way, or maybe all 20 are coming together. Okay, so it
Alright.
depends. Any type of the amino acids, like 2 are repeating again and again, 3 are repeating, 5 are repeating, all 20 are repeating. It depends which protein we are talking about. They will have different pattern according to that. Okay, one very important point that we missed, let me just tell you, that is the property of addition and condensation polymers. One thing, let's go back to the addition polymers. How you can identify quickly in the exam, it's a trick that I'm going to tell you. How you can quickly identify that a given polymer to you is addition or condensation. For the addition one, you will always have, always, it's a must thing. You will always have just carbon-carbon chain in the polymer. Only carbon-carbon chain is going to come in the polymer. Nothing else. Carbon single bond, single bond, single bond is going to come in a sequence. So what you can say, it's a carbon-carbon backbone in addition polymer. It's a must thing. If they have given you 2 different polymers and asked you to identify which one is addition, which one is condensation, rather than wasting your time in just checking the monomers, just see if it has carbon-carbon backbone. No need to check anything else. It's confirmed it's addition polymer. Okay. In comparison to this, if you go to the condensation polymer, you will see different backbone. Let me show you one of the condensation polymer, this one. If you, okay, over here it has the boxes. If I show you without the boxes to make you more clear, let's check out this one without the boxes. If you check out now, this is the backbone. Hydrogens are hanging, so ignore the hydrogens. This backbone has carbon, then 6 more carbons, then carbon, then oxygen. So oxygen is something different. So it can have, in carbon-carbon chain, it can have carbon, oxygen, sometime nitrogen, sometime anything else. If multiple things are attached in the backbone, not only carbon-carbon, it can be any oxygen, any nitrogen, except carbon, multiple other things are attached in the backbone, in the chain, it means that is condensation polymer. That is not addition polymer.
Miss, can you repeat for the condensation polymer?
For
Just
the
one last.
condensation, it's not only carbon, it can be anything else with the carbon. Like if you just check out this hole, it has 1 carbon, then 6 carbon, okay, fine, then again carbon, but oxygen. Again, over here, one more oxygen in the chain. If chain has anything else than carbon attached, it means that is condensation polymer. In
Okay.
addition, it will be just carbon backbone. Let's check out one more addition. It will be clear to you how for the polyamide we can check. Yeah, this one. We just remove this one and show you the backbone of this polymer. This polymer has the backbone, this one. Ignore even the boxes. No problem to check the boxes even. Without the boxes, you will get the answer. It has carbon, then see, it has nitrogen. Then if you move, more nitrogens. So it's not just the carbon, it has something else attached. So it means that is condensation polymer.
Okay, Miss.
Okay, so that's a trick to quickly identify if a polymer is condensation or addition. Okay, that's the end of the lesson. If you have any question, you can ask. Otherwise, the lesson is over.
Submarine, you have a question?
Yes, Samreen?
Oh, yes, Miss. Miss, I'm sorry, but could you please repeat the definition of amine and amide? Because what's the
Amine
difference between
and
them?
amide. Yeah, amine was having just the NH2 group. If NH2 group attached with anything is there, that is going to be amine. If C double bond O, NH is there attached on both sides with something, that is going to be amide.
Okay, Miss.